Hi there, welcome to Mini Math Lessons with Karen. Today I'm doing two activities that deal with proportional reasoning, and we're going to be looking at a simulation and then comparing things graphically and with tables. So the first activity, well first let me just talk real quick. I am using Classpad.net, free web-based mathematical software, pretty much does everything you need, calculating, graphing, geometry. You're going to see a lot of that in these activities. You don't have to have an account. You could start playing with these activities, which I've shared the link in the description below. You can just start playing with them, but when you're doing that, you're in as a guest, and so maybe some functionality doesn't work because you're in the guest mode. So if you find there's an error, it's usually because you're in guest mode. So I would suggest creating an account. It's completely free. Once you have the account, then all the functionality opens up. And you can also save and modify and change things as you want. So my suggestion is create an account. It's free and it's fantastic to use with any math that you're doing. So let me get into the first activity. This is an activity where they're going to be really kind of connected to what happens in the real world when people do, when they say there's so many rhinoceroses left in the world or there's so many tigers. They didn't actually go out there and count them. They tend to do an estimate, and they do proportions, using a proportion. So there's an example up here at the beginning that basically says, they tag the animals and they put those animals that are tagged back into the environment. And then they take several samples where they catch a certain number of animals, count how many of those are tagged compared to how many they caught, and then they use equivalent proportions, equivalent ratios rather, to make an estimate for that population. So they're going to do a simulation like that. So as you scroll down, they're going to see that there's this simulation of a lake full of fish, and we want to find out how many fish are in this lake, get an estimate. And so this simulates catching fish. So the red circle here is controlled by the sliders, and it simulates catching fish and counting how many are tagged. So that are marked, as we've put it here. So M stands for fish that are marked, and C stands for fish that are caught. And there are 15 fish that we know they went and they caught. They marked 15 of the fish, and then they released them back into the pond, and now we're going to take several samples. So as they go down here, there's a table where they're going to be recording their catches, and they're supposed to do at least 7, right? So there's 2 already recorded here, and you'll notice that this is keeping track. So what we're going to do first is let's just show you how you would use the simulation to catch another set of fish. And so we're just going to move, and notice how as I move that changes the net's position, basically. And so then after I've moved both, I come down here, and this stands for 7 is the marked fish, and this is how many we caught. So we're going to record of the next catch of those 137, 7 were tagged. And then they can do some calculations. What's the ratio of tagged to caught? And so we could use our calculator here. That's all I'm doing is just the calculator, and put that number here in the ratio, and then change that ratio to its percent. So we have a 5% tag to caught ratio. And then as they collect more and more data, what they're then going to do is, let's get rid of this from last time, is try to make some predictions. So if we just use our first ratio, and here's where it's nice in the text sticky, you actually have ability to do the proportions. So let's say we just use our first one. So let's say we took one sample, we want to see what that is. So we know we have 15 tagged, and so I can use the template here, or I'm just using my computer, and we caught 3 that were tagged out of a total of, I think the first sample was 69. So let's put 69 here. So that's my first. So if I just use that one sample, what would my prediction or estimate for the number of fish caught be? Well, I would however I decide to calculate this, I would guess that there's 345. So is that an accurate estimate of how many fish? So then, oops, I And so then you continue to do that. So you're going to test each sample and make a prediction, and then you're going to test the sum of the samples. So if we did the sum, you can use your quick way to do this. And obviously we haven't collected enough here, but let's just do the sum of the marked over the sum of the caught. Oops. Capitalization works here. And so now my ratio is 11 over 298 compared to 15 over x. And then let's check the estimate there. And so what makes sense for the number of fish caught there? Was 345 our first estimate a good estimate? What's our estimate now? So maybe we're going to do so I have more fish here than my original estimate. So is it more accurate? So they're going to be testing that. So that's what this first activity is about. The next activity is comparing. We have two students, two girls growing plants, and they each started with a plant of a different size, and they're comparing how far they're growing. And so the first girl, Alicia, had 60 centimeters and it's now 100, and the other one had a 25 centimeter and it's now 50, and each one claims that their plant's growing faster. So then how do you make that argument? So it's really just first prove convincing argument that Alicia is growing faster. So she's the one who went from 60 to 100. So this one, they're going to collect data, and they're just going to basically look at the constant rate of change is what we're thinking about here, ratio proportion. And you'll notice that as they do it, it does look like graphically, and then we might even do proportions and show that it does look like Alicia is growing faster if we're looking at the constant rate of change. But if we then do rate of change over time comparison, and this time we're going to use equations, we can prove that Bernice is correct. So basically they're doing an algebraic argument and then a geometric sequence. So an algebraic sequence and a geometric sequence. And so in this one, they're thinking about the rate of change. So like the first one is her first time she measured it, it was 100 minus what it started at, and then the rate of change over, sorry. So she has a rate of change 2/3, or 1 plus 2/3, and then the other one went from, and let's actually start with our fraction here using our template. So 50 minus her start height. So if we just look at that, this is changing faster, right? So how could we then graphically use an equation to represent them? And so that's what they're going to go do here. So the first person is 60 times, each time it's going up by 1 plus, and our, whoops, let's get our template out here, minus over 60 raised to the however many times we're doing a measure, right? So we're going to raise it to the x power. And then we're going to look at the other girl, and hers is 25. So each time is going 25 times, oops, I didn't mean to put an x there, times 2. So it's going up twice as much each time. And so if we look at it that way, I think I did that right. Oops, here's my problem right here. I have an x, not a times. Let's say that doesn't look right. There we go. So now if we do it by looking at the rate of change over time, you'll see that Bernice is actually growing at a faster rate. Like originally, yes, the first one, Alicia is growing, but at some point then Bernice supersedes. So it's sort of just which way are you thinking about it, and depending on how you think about it, each of them has a logical argument, and that's how it ends, is show how each one can have the correct argument based on the mathematics you're using, and then which one would you pick, their argument behind that. So just different ways to use proportional reasoning to make arguments and to estimate populations and really use them in realistic situations.